Assalamualaikum and greetings. We are from Group 4 presenting our mini project poster titled Magnetic Vector Potential in a Solenoid. What we have studied and investigated are the magnetic field B and the magnetic vector potential A around a current carrying solenoid using both computational and experimental style visualization techniques. Rather than focusing only on the magnetic field, this study emphasizes the role of the vector potential as a fundamental quantity in electromagnetism. In a solenoid, the magnetic field is known to be strong, nearly uniform, and directed along the axis inside the coil, while the field outside is weaker and more spread out. However, this magnetic field alone does not fully describe how magnetic effects are distributed in space. By studying the magnetic vector potential, we are able to visualize magnetic flux linkage and understand how the magnetic field is generated by the current flowing in the solenoid windings. Another important objective of this project is to explore the concept of gauge freedom. Since the magnetic vector potential is not uniquely defined, different mathematical forms of A can represent the same physical magnetic field. Through our simulations, we aim to show that while the numerical value of the vector potential can change, the magnetic flux density remains unchanged, reinforcing the idea that B is the true physical observable. Overall, this project aims to strengthen our conceptual understanding of the relationship between the magnetic field and vector potential, and to demonstrate how computational modeling can be used to visualize and verify key principles in electromagnetism.
So I am presenting the methodology of our mini projects, which I am in charge of. So for the simulation setup, a finite length solenoid was modeled inside an air domain using COMSOL multiphysics, which is a magnetic fields interface. And due to geometrical symmetry, only 1/4 of the solenoid was simulated to reduce computational costs and while preserving the physical accuracy. And then the solenoid axis was aligned along the z direction. For excitation and physics, a steady current was applied to the solenoid windings to generate a magnetostatic field, and where the simulation solved for the magnetic vector potential, which is alpha, from which the magnetic flux density was obtained using the formula beta is equals to delta multiplied with alpha, where a virtual Hall probe was placed along the solenoid axis to measure the axial magnetic flux density, which is Bz. And then the azimuthal component of the vector potential, which is alpha phi, was extracted for visualization. For the last one, which is visualization and analysis, surface plots were used to observe the spatial distribution of A and of alpha and B for beta. So contour plots were used to visualize magnetic flux linkage within the solenoid. And for the last one, gauge freedom was demonstrated by applying a constant offset to alpha and recalculating the resulting magnetic field.
First of all, I will talk about the magnetic field and magnetic flux density. Graphic shows a solenoid cutter cross-section where the black streamline acts as magnetic field of solenoid, while the colored contour shows the magnetic flux density. The next graphic shows a 3D model of solenoid surrounded by simulated air. Red arrows indicate magnitude and direction of magnetic flux, obeying the right-hand rule. When current flows through a solenoid, it produces a magnetic field that is mainly axial, meaning it points along the length of the solenoid. For this reason, we focus on the Z component of the magnetic flux density, Bz, which is measured using a virtual Hall probe. The results show that the magnetic field is nearly uniform in the central region of the solenoid, while it becomes weaker near the end and outside the solenoid due to finite length effects, where the field spreads out and partially cancels. This behavior closely matches theoretical prediction for a finite solenoid, confirming the accuracy of the simulation. Next, I will discuss the magnetic vector potential. Graphic shows the solenoid quarter cross-section, where the colored contours shows the magnetic vector potential. The next graphic shows top view of 3D model of the solenoid surrounded by simulated air, where red arrows indicate magnitude and direction of magnetic vector potential, parallel to the direction of flowing current. The magnetic field is related to the vector potential by the equation B equals to delta times A, which makes the vector potential a fundamental quantity in electromagnetism. In a solenoid, the electric current flows azimuthally around the windings, and as a result, the vector potential is also azimuthal, while the magnetic field remains axial. The simulation shows that the vector potential is strongest near the coil windings and decreases with distance, reflecting the current distribution. When we calculate the magnetic field from the curl of the vector potential, the result overlaps exactly with the directly computed magnetic field, verifying Maxwell's equation. Finally, visualizing the vector potential provides insight that is not obvious from the magnetic field alone. Contours of the vector potential clearly show magnetic flux linkage, and a gauge transformation changes the numerical value of the vector potential without affecting the magnetic field. This confirms that while the vector potential is not unique, the magnetic field is the true physical observable. Overall, this study demonstrates how combining magnetic field and vector potential analysis gives a deeper understanding of magnetic field generation in a solenoid.
To conclude, physically, this project shows how the magnetic field is a solenoid arises from the structure of the magnetic vector potential. In a current-carrying solenoid, the electric current flows azimuthally around the coil. As a result, the magnetic vector potential also exists primarily in the azimuthal direction. When we take the curl of this vector potential, it naturally produces an actual magnetic field inside the solenoid. This explains why the magnetic flux density inside the solenoid is strong, uniform, and directed along the axis, while outside the solenoid, the field spreads out and weakens. Even in regions where the magnetic field is small, the vector potential remains non-zero, indicating how magnetic flux is linked throughout the system. By comparing the magnetic flux density with the curl of the vector potential, we verified the relationship B equals curl A is satisfied everywhere in the model. The perfect overlap between these results confirms that the simulated fields are physically consistent with Maxwell's equation. We also demonstrated gauge freedom by shifting the vector potential by a constant. Although this changed the numerical value of A, the magnetic field remained unchanged. This confirms that the magnetic flux density is the true physical observable, while the vector potential is a flexible mathematical quantity that describes how magnetic fields are generated and linked in space.